Brought to you by Chemistry.
Hi everyone, and welcome to Brought to you by Chemistry. What's brought to you by Chemistry, I hear you ask? Complicated reactions? Complicated exams? Even more complicated romances? You know, the ones that most people wouldn't understand, but it's okay because you have blind faith that it will work this time. I mean, yes, but in this case, Brought to you by Chemistry is a podcast series from the Royal Society of Chemistry, so you see the branding there. My name is Dr. Alex Lathbridge, and in this series we are back and better than ever because we're taking a look at batteries, bringing together experts from inside and outside the world of chemistry to help us understand the ins, the outs, the ups, the downs, the positives and the negatives of all things battery. Wonderful guest. Could you please introduce yourself?
Yeah, sure. My name is Dr. Sarah Gordon. I am a geoscientist, but I also work a lot with sustainability and environment, social and governance, both through my consultancy that I run called Satarla and also through a not-for-profit called Responsible Raw Materials.
Second wonderful guest. Could you please introduce yourself?
Hello, my name is Frances Wall and I'm Professor of Applied Mineralogy at Camborne School of Mines in the University of Exeter. I have a geochemistry degree. That's where I started at Queen Mary College in London. Then I worked at the Natural History Museum, and I'm now moving from geology and mineralogy type things to talk to all kinds of other scientists about circular economy.
Wonderful. My name's Alex, and I know neither of these things, but by the end of it, I will know perhaps a little bit more about it. Today, we are chatting about mining when it comes to batteries. So I guess my first question for both of you is, what materials do we actually need to make a battery? Sarah, start with you.
Excellent. So to go into a battery, we need all kinds of lovely materials. Depending what the battery is made of, we might need some lithium, we might need some graphite, we might need some cobalt, we might need some nickel. Frances, what else do we need?
Yes, well, of course, there are major metals that we call them as well. There's aluminium and iron and, lots of other, main materials in batteries. But I want to stick with those more exotic names that you just said, Sarah, like the lithium, the cobalt, the nickel, the graphite, because they're what we call technology metals, and some of them are also critical. So they're in restricted supply, but really economically important. And for batteries, we need so much more of these, don't we, Sarah, than we've ever used before. So more than 10 times as much lithium in the next 20, 30 years to make the number of batteries that people calculate we need for electric vehicles and energy storage. So these are exciting times for geologists to learn all about these new elements and, their geochemistry, how they get concentrated into ore deposits.
Okay. So with that, just looking at the technical process here, what actually is the process of mining when it comes to these elements? Like, how does it work?
So when you want to, say, go and find some cobalt or some graphite or some copper or some iron ore, it all starts with looking at a geological map of the world, really. So you say, okay, where do we think we might actually find these materials? Because, of course, those materials have been concentrated through natural earth processes in different parts of the Earth's crust. So as a geologist, we look at a map of the world and we say, right, I am looking for some cobalt. Where do I generally know from my geological and geochemistry experience, where in the world might I find that? So we look at things from a technical perspective first, and then we very quickly layer on top of that all of the political, the social, the environmental, the infrastructure layers of data, because it's not just about finding those minerals and metals in the ground. It's also saying, well, can we actually, if we can extract them, can we do it in a way that doesn't negatively impact on the community and perhaps provide some development? What about the environment? Is it in a place that might be incredibly special with regards to the biodiversity? All of those different aspects layer in on top of it. And once we have all that data, we then say, okay, now do we go and take something like a drill rig, for example, and go and say, well, let's take a look at the rock and the ground. So what happens in exploration is a huge amount of remote work first, where we say, where in the earth might we go and find that rock? Once we think we've maybe got a bit of a location, we then go in and we do a whole load of different sampling. And that might be geochemistry sampling, where we might take water samples, rock samples. We might take cuttings of plants, for example. They can all give us an indication of what might be in the ground. We also use a lot of geophysics techniques. So we might use different types of seismic, for example, and different types of using the quality and the properties of those different elements to say what might be in the ground. And once we've built up that model with more and more data, we get to the point where we say, okay, do we now go and raise some money to begin to design really what the mine could look like? This process can take a long period of time. So going from actually discovering some rock in the ground, that happens obviously after you've gone and looked for it, but going from discovering to opening a mine on average takes 30 years. In short, the process or the value chain for mining is often referred to as initially you have exploration, where you go and find the rock. You then have a development and a building phase where you design the mine and you actually build it. You then have an operational phase, and all the way through these different phases, you are rehabilitating that land. You're getting it ready for what happens after you've extracted those materials and those commodities from underneath the Earth's surface.
Okay. I mean, obviously there's a lot happening there, and you sort of mentioned it very briefly, but I sort of want to touch on it sort of first with you, Francis. In terms of the environment, talking about mining as it's done now, I mean, what are the impacts there? What are the impacts of this process on the environment?
So there are a variety of environmental impacts that we think about and to take into account. So let me start off with a chemical one, I guess. And that's an important point, that we're quite lazy as geologists. We talk about a cobalt mine or a lithium mine. But the first thing to say, of course, there's no lithium metal sitting in the earth, and there's no cobalt metal. You can't just go along and pick up cobalt metal. So what you get is actually some often very beautiful minerals like carolite or heterogenite, names that we don't bandy around for maybe obvious reasons there. But so the metals are held within minerals in the earth, and they sit in the rocks. And so we have to work out how to get those out. And along with those metals come other elements, for example, sulfur. And that's why I've picked on this topic under your environmental question, is because when you have minerals with sulfur, they can make rather acid waters, and you get this phenomenon called acid mine drainage if you're not very careful. And that's a really important environmental factor around most of the sulfides, which would be for batteries, nickel deposits, and many of the cobalt deposits would have to be very careful about that. So you have to work out what the composition of your ore is. So that's number one. Are there any potentially harmful elements sitting there that you need to make sure you look after on that mine site and keep within the mine site and make sure they lock up and don't pollute? Then other really obvious ones is the mine it may be an open hole, so a quarry, an open hole in the ground, or it may be deep underground, but you will likely have some surface impact. So you have to work out what's on the surface now. Is it fields? Is it forests? How are you going to account for taking that away? Is it something that's easy to put back afterwards, or is it something very precious? I always like the example of one of the bauxite mines in Western Australia that employed 3 geologists to look after the ore deposit and 10 times as many biologists to look after the environmental effects of their very precious Jarrah forest and make sure it went back on again after they finished mining. And then, of course, you look at other environmental effects round and about. What happens if you're with rivers and things? Where will they go to? Will you move anything? What are the longer term and wider environmental impacts? And you probably have people looking at that over a year or so, because you'd want to go through all the seasons to check what's going to happen. What's the biodiversity there? Is it on a migration route? Is it special for some kind of other environmental reasons? So lots of different factors, and that's some examples of them.
Obviously, there is a lot going on there. And I guess when it comes to mining itself, and we talk about it in sort of a sort of more detached way, who is actually doing this mining as it stands now? Because, I don't see lithium, nickel, bauxite. I don't see those mining jobs when I look on LinkedIn or Gumtree. So who is actually doing this work?
So I think with that, you get, so there are a number of large scale mining companies in the world. And the places that you will generally see their jobs being advertised are in the countries where they're actually mining. So, for example, some of the world's largest mining companies are based out of Australia or Canada, for example, and that's because there's lots of mining activity that goes on there. But then similarly in Africa, Latin America, all the way through Asia as well, we don't tend to do much physical mining here in the UK, which is why you perhaps don't see those jobs advertised all of the time. So you get in the large scale mining sector, these are the companies that you see listed on the London Stock Exchange. These are the ones that you hear people talking about. But the vast majority of people who work in mining are undertaking artisanal and small scale mining. And this might be as small as, sort of a mother and son type activity, maybe with some sort of digger, maybe not, and they might be looking for gems or something like this. And of course, that can be happening anywhere in the world. And what we see is that I think at the moment, I'm not sure exactly the numbers, but there are probably 2.5 million people employed in large scale mining. But then there's, at least 30, 40 million, maybe many more than that, engaged in artisanal and small scale mining activities. And as I mentioned, they could look like anything. It could look like a small quarry here in the UK, all the way through to precious metals or diamonds, for example, in different parts of the world where you might find them.
Yes. And don't forget too, although the big mines may not be here in the UK, there are certainly some. We have some very special potassium for fertilizer mines. We're digging up basic things like rock salt, some good chemistry for you, fluorite. We're doing here gypsum. We do some of the world-class China clay mines are here. So these are all employing people. They're good jobs for the local people. And then the specialists as well, like the geologists and chemists and mining engineers. And there are big well-known companies who work in the UK who carry out consultancy work, and perhaps especially the kind of environmental impact assessment that we're discussing here as well. They do that all over the world because we have some really good expertise here in Britain. And they also often take that expertise and move away from the field or the laboratory into the centre of London and advise in the centre of mine finance that is in the capital of the UK here. So this is a real world centre of mining in London. And so there's lots of people that translate their skills out to the practical ones. Maybe they did in their degrees, and then they go and advise on mine finance and insurance, and maybe they do HR. And women in mining, how many members are in Women in Mining at the moment, Sarah? I'm not quite sure, but I bet it's over 1,000 people in Women in Mining based in London, maybe 2,000, is it?
Yeah, definitely. And I think with that as well, so you have lots of specialists here in the UK. So at the moment, lots of people are working with the financing companies and also the mining companies, especially on climate change, because with regards to mining, not only are you extracting the materials out of the ground that we need for the wind turbines, the photovoltaics, the batteries, but we're also we're basically being stewards of assets that are incredibly long time horizon assets. You're looking after this mine potentially for hundreds of years. So all of that needs to be considered. But also with regards to groups like Women in Mining UK, Women in Mining International. In the UK, we have some fantastic experts on the social side of mining. So it's not just the environmental, it's the social side. So that includes aspects of human rights, different labour rights, bribery and corruption, fraud, etc. So all of those aspects of corporate governance, for example, that are really important to make sure we get right. And that's because with regards to the energy transition, mining, perhaps unlike many other sectors, has the potential to unlock the ability to distribute wealth around the world in a way that other sectors might not necessarily have the opportunity to do so. So if you're mining cobalt in the DRC, if you can do that in a way that's responsible, That is huge with regards to ensuring a just energy transition with regards to the people side of it as well.
So, I mean, with that, I mean, it's all well and good, talking about sort of more equity and, or looking at it from the perspective here in the UK, but, talking about the fact that, you've got companies, mining companies that are being traded on, the London Stock Exchange or internationally and stuff. But then you look at the actual people who are doing it on the ground and they don't really see that money. I mean, I found it quite interesting that you described it as sort of artisanal, like one would make bread or something. When, there are real human rights abuses there. So how can mining companies, I know sort of, it might sound a lot harsher. I say it sounds a lot harsher, but how, when it affects people in Latin America, it affects people in Africa, people who might look like me, like how can we sort of say mining can be done ethically? How can we spin that into an ethical way?
I want to jump in and unpick what you've said there a little bit, because that's really interesting statements. First of all, let's pick up about the 100 million people in the world that rely on artisanal mining. So maybe the figure Sarah said, I think is about right, isn't it? About 30, 40 million people actually doing it. But remember, mining is as fundamental as farming. It is the fundamental thing that humans do. We use the earth, we grow stuff, and we pick up stuff, and we have been doing since the Stone Age. And so I think a view of artisanal mining as something that's inherently bad, first of all, is just categorically wrong. So there are many people that do it. Some people do it and would continue to do it, and they do very well out of it, and maybe they're selling gemstones and things. Some people only do it because they're utterly desperate. They've got no other way of making their living, and they're right on the edges of society, and that needs looking after, if you like. Some people are exploited into doing it, but all of those things are true, and there's no one picture of artisanal mining. There are some fantastic fair trade gold schemes, for example, and gemstone schemes where you can actually buy materials, just like fair trade with coffee or something. You can buy things that is helping people in livelihoods in small scale mining around the world. And that's where most of the miners are, but that's only very much a minority of where the metals are coming from. So looking at the computers in front of us, the majority of the metals or mineral goods that made those computers, they were mined by industrial scale mining. So most of the stuff is industrial scale mining. And there is a whole nother world, hey Sarah, of people doing brilliantly well for the people who work for them. It's one of the main ways, you can get sustainable development all around the world, often into countries that have very little other industrial infrastructure. If you can make your mining work, then you can really make it help locally and nationally. And if it's the other way, it can be a complete disaster. And everything exists, from the very good examples, hey Sarah, to the really bad. And we could spend another workshop worth trying to talk some more about that. So everything's there, high stakes, certainly for the energy transition. People want a part of it, whether it's copper or lithium. And it's really important that there's I think, excellent choice by the manufacturers who are buying these metals to make sure they're responsibly sourced, and they're doing things around the world for people that are positive and ensuring their sustainable development.
You're talking about these large companies who are doing a lot, and you're talking about corporate responsibility, but like obviously for these companies that are working internationally, in some places around the world, they might be getting better, like they might be having better responsibility, trying to do it more ethically, really trying to sort of give back to a community. But in other areas, in other parts of the world, that could be, if not directly, then indirectly through other companies or people who manage things on the ground, it can be not so ethical. So how can the two sort of be balanced? Do you know what I'm trying to say? Do you get what I mean?
Yeah, exactly, Alex. And I think, this is the case exactly as Francis mentioned there. There have been some absolutely horrific things that have happened in mining in the past. There are some terrible incidents that have occurred, and there's some incredible social injustice that has been created, in part because there's immense wealth in the grounds. And as is in human nature, often what happens is some people strive to keep that wealth and other people lose that wealth. And this is not in line with the ambitions of the just energy transition. And so what you're seeing at the moment is increased focus with regards to how do we ensure that mining as a sector is carried out in a responsible way. And that is being really addressed through accountability. So accountability on the mining companies themselves to ensure that they operate in an ethical manner that's in line with the values that they all state. So do they actually deliver on what they say that they're supposed to be doing? But then also as well, scrutiny that is applied to that by the investors. So the investors, of course, I mean, now increasingly we're asking those investors to invest in sustainably aligned manners and ESG aligned manners. And those investors that are investing in mining are requested through the stewardship laws, really, to make sure they understand where that money is going. But then also as well from the customers of mining. So this comes into the responsible procurement aspects, as Francis was saying just now. So if you are Elon Musk with Tesla, for example, there's a huge assurance mechanism that goes on to say, well, where does that cobalt or lithium or whatever come from that then ultimately ends up in a Tesla vehicle or whatever we might be looking at. And those are just three of those different avenues where people have got something to gain from ensuring that the materials are extracted in a responsible way. You've also got immense change going on, say, at government level. So at the moment, the UK government is ascertaining what is our minerals strategy in the UK so that we can make sure we can build those wind turbines, etc. So what can governments do with regards to this? So it's a multifaceted solution really to a problem that we cannot hide from, because mining has done a lot of damage in different parts of the world, but we have to make sure that we mine responsibly in the future, because we need huge volumes of rock to be extracted from the ground and processed. And some of those processing techniques are really, really difficult with regards to the chemistry that needs to go on in there. How do we do that in a way that optimizes the impact that we can have on the environment? So it looks for the good stuff rather than causing bad stuff to happen.
Can I jump in with some chemistry? So we often talk about supply chain assurance. And of course, that might be an obvious thing, is to say, well, can you use some chemical signature, some chemical device of some kind to actually track, from the mine through the processing. And the challenge, chemists out there, is it's not easy because, as we said, things start off in minerals, and that's really easy. Well, it's easy if you have the right kit. They managed to do it by Colombo tantalite, which was coming out of the conflict zone in the eastern DRC. If you do enough chemistry on that, you can pretty much track back to the mine it came from. But the problem is that then normally the mineral will go into either a smelter or an intense chemical process to extract the metal from the mineral. And then how on earth do you track it from there? So that smelter or processor is an absolute key stage. Talk about white smelters sometimes, knowing that they are checking what's coming into them, because there are ways and means of doing that. And if they're careful enough, then the customers that buy to make the metal products and go on into making the batteries, they can be sure that if they're buying from that smelter, it's okay.
I think that's really that one's a really fascinating point. And sort of the two bits you were mentioning about the sort of chemistry and this, because, again, I go back to it. I sort of think about like how you've got neo-colonialism and in sort of Africa around lots of various other countries in the world who are taking advantage of the continent. Going forward, can we make a mine that is more sustainable and a mine that will allow people more easily to companies to more easily say, I can definitely be sure that this has come from a mine that is sustainable because it has this specific marker, which means it was set up in 2022 onwards. Do you know what I mean? Something like that, where you can say at this key point, I know we've made a transition?
Yeah, so I think with regards to this, and I'm acutely aware that we're speaking to lots of lovely chemists who understand the periodic table to a much greater level of depth than I do, perhaps. And this is something where the processing of every commodity is different. So some commodities will go through smelters, others won't. And so depending on what the commodity is and what you're trying to do with it, so what product effectively you're trying to create, some of them will have a chemical signature that will then stay with that particular commodity. And so you can track it. Others, as Francis has just mentioned, there will be points in that value chain. So if you have lots of different material coming into a central smelter, the chemical process there effectively means that any unique signature from where on earth that got mined will get lost at that point in time, just through the chemical process that it's going through. So that's something there where the actual chemical signature may be lost to some degree. You may be able to tell which smelter it's coming from, but that's where the paperwork comes in. That's where something like blockchain begins to help us, and it goes into that ledger and it tracks that particular commodity through. There are the next exciting thing then is when we begin to bring in recycling into this process, because, for example, rare earth elements, and I know that Francis is probably one of the world's experts with regards to this, but I'm going to tiptoe into this area and then hand across to Francis. Rare earth elements come from many different parts of Earth. So the main thing is that they're not rare, but as we know, they are incredibly difficult to process. There's a reason why most of them fit into the same box, effectively, from the periodic table.
I mean, you keep calling them rare earth elements, and now you keep saying they're not actually rare. What are you doing? I feel as though both of you have come into here and just turned this podcast into a place of lies. Why are you doing this?
Why are we doing this? Well, then...
Do you want me to? I know.
On you go, Francis. I will relinquish the floor.
It was the chemists. There we are. It's the chemists' fault about rare earths. They called the rare earths rare because they're extremely difficult to separate from each other, and that was the word they chose. So don't blame the geologists.
I like that you've come onto a podcast by the Royal Society of Chemistry and gone, you know what, chemists, you're to blame. You're the problem. We've turned it from, hey, consumers, if you cared so much about this, then you would actually ask where things came from, to, now, you know what, chemists, they're the problem.
Yeah, so with that as well, in terms of, okay, so let's do some myth busting, shall we? So rare earth elements are not rare in terms of their occurrence on Earth. You get them in loads of different places. So from a geology perspective, it's actually quite easy for us to go and find them. The bit that's difficult is where we hand over to the chemists and the engineers is to actually separate them out. So that's perhaps why they are rare, because it's rare to be able to separate them into the different component parts. Another thing where there's a bit of a myth busting here is in terms of are we running out of these critical resources, etc., in Earth? Well, there's lots of them. Again, it's just difficult to process them, and so therefore be able to get them into circulation. So at the moment, when we start talking about things like recycling and the circular economy, it would be amazing if we could build all of the batteries and wind turbines and everything from material that was already in circulation and was already available. But at the moment, we are millions and millions of tons worth away with regards to the amount of lithium or cobalt or rare earth elements that are in circulation at the moment to be able to build the wind turbines that we need for the future. So we need to be able to responsibly extract this material from the ground for many, many years to come to actually ensure that we've got enough stock in circulation and available, i.e. a wind turbine that's at the end of its life, because then we can now start to recycle it to then bring it into that full circular economy.
Okay, so this is actually really fascinating. I think this is one for you, Francis, because I sort of when you've been talking about it, my brain's been percolating this. Like, you know, we've got these minerals, and you know, like they are being processed. I mean, I'd like to first know how the processing happens, but I guess for me and the listeners to this podcast, how can chemistry make like this process greener? Can it be made like greener? Can it be made more Better, more better is the phrase I'm going with. More better. Please, Professor Francis Wall,
Yes.
get
Okay.
my brain, the
Right.
words
Let
I
me
say
think.
better.
Let me give you some information and then a chemistry challenge as well. So first of all, how do you separate the minerals from each other? So on a mine, you'll get minerals, and this is the area called mineral processing. Basically, you have to find the properties of the minerals that will allow them to be separated. And that could be anything. It could be their size, it could be their shape, it could be their density, it could be their solubility. And mineral processors will look at anything. And basically, if you can do it physically by, say, magnetic, that's a good magnetic property, or density, that's normally cheaper than actually going to the chemistry bench to separate things out. So you wouldn't do physical things first. Normally you have to crush the rock, and of course, most rock is pretty tough, so that uses quite a bit of energy. Then you do clever things to work out how are these minerals different that I want to take apart. Maybe it's color on an optical sorter, just pinging them one way or the other with a puff of air. Maybe it's magnetic, or maybe it's chemistry. And so you normally come on eventually to chemistry. There's a very important process called flotation, where things are hydrophobic or hydrophilic, and tiny little mineral grains pop onto bubbles on a froth and get taken over the top. So there's hugely inventive science been going on here, and a lot of that is very clever, and it's always looking out for ways to get even cleverer. And if I come back to our rare earth element or lanthanoid example, this is where we need chemists to get even cleverer. So we can take the minerals out of the rock, and then you have to dissolve up those minerals, and that normally leaves a lot of mineral acid, and normally the embodied carbon in mineral acid is pretty high, so that will really put the carbon footprint of your deposit up. The more acid you use, the worse for that. So I suppose we need low carbon acid manufacturer for a start. Okay, so obviously renewable energy going into that, I guess, but also new types of things that can dissolve minerals up. So we work with a group at Leicester University who are using chemicals called deep eutectic solvents. They're very straightforward chemicals, and they have a much lower environmental footprint than things like the mineral acids. So there are chemistry groups already in the UK, others besides, not just at Leicester, but other places too, looking exactly for how you do that. Bioprocessing is another thing we're very good at in the UK. Can you use microbes in your chemistry to actually help munch up the things, either the minerals you do want and take them away in solution, or the things you don't want and let the minerals fall out of that? So lots of chemistry going on. And perhaps the hardest challenge of all in our lanthanoid or rare earth chemistry is separating those elements from each other. That is a process that needs hundreds of steps in the normal solvent extraction process. It's really inefficient. And if a chemist would please like to invent us a really easy way of, much more effective way of separating those, that would revolutionize the industry. And what else? I was going to do one other thing. Yes, I think the other challenge for chemists, then I would say, and I'm going to pick the rare earths again because there's such a nice series. Everyone will know lanthanum and cerium. There's everyone in all chemists are likely to know lanthanum and cerium. There's as much cerium on the earth as there is copper. Neodymium we all need in the permanent magnets that make direct drives in cars. So they're not in batteries so much, but they're in most electric vehicles. And then there are other rare earths like thulium that very few people will have ever heard of. And so for chemists, please never invent anything with rare earths that are what we call the heavy rare earths and are in tiny amounts and really are precious things, because that gives us a real tough challenge as geologists to go and find them. Carry on using neodymium magnets. They're fantastic materials. They do so much for us. That's a whole nother podcast for you sometime.
So with that, and I think this is a case of whenever we're trying to extract something from the ground, we generally have all of this, we call it waste rock. nothing's waste. It's all material that could be used for something. And I think, as Francis is saying, our problem is that all of the lovely inventors of the world keep using the difficult materials that are really difficult for us to extract. So instead, maybe as part of the specification, rather than thinking, hey, we've got the whole periodic table to play with, actually go for some of the stuff that's easier for us to give to you. The other challenge as well is, as Francis mentioned, a huge amount of energy goes into smashing rock up. So we can then use all of the fabulous different properties and characteristics to separate out those minerals and bubbles and magnets and everything else to do that. If we can extract the material from the ground without having to smash rock up, and so some organizations look at leaching material out of the ground, which on one hand is great because it means that you can basically dissolve out the minerals that you actually need and collect them. So it sounds fantastic, provided you can do it without contaminating all the groundwater. So again, it's like, okay, I'm going to reduce my carbon footprint because I'm not having to dig the rock up and smash it up. But at the same time, I might be creating an environmental disaster because I am dribbling a load of acid into the ground. So we need to be able to work out how can we extract the minerals and the material that we actually need from the ground, actually in the laziest way possible. And chemists, I'm not saying that you are lazy, I'm saying that you are clever. So please help us as geologists to be lazy.
So, I mean, you both said really interesting things there. And Francis, to come back to the point you made earlier, about as consumers, do we ask where things, if things have been sourced ethically and stuff? But I guess from what both of you have been saying, these sorts of technologies are everywhere in life. They're in your cars, in your phones, your computers, the screens, like everything we do, So if it's not just down to us as consumers, if this technology and sort of these metals are such a part of our daily lives, is there something that we can do, perhaps with chemistry or maybe some sort of expertise, to recycle, the chips that we have now, to recycle the things that contain these rare earth metals that actually aren't that rare? How can we move away potentially from having to do all of this new work into mines? Is that something that people have considered? That sounds so easier.
Yes.
Have you considered just recycling? Have you?
The answer to that is yes, certainly people have considered it. And in some of the major metals, then the rates of recycling of aluminium, for example, are actually pretty high. But if you come to lithium or neodymium, some of these very specialist things, then the rates of recycling are still really low. And there's a variety of reasons for that. They may sound very glamorous, but they're not very expensive. If you have something like gold or platinum that really is expensive, then you'll find the recycling rates actually are pretty high because it's worthwhile people getting them. And I think that's a challenge. That's a really good chemical challenge. As we bring new lithium into the system, new neodymium into the system, let's be careful with it. So we do have a technology metals circular economy centre called Met4Tech, met4tech.org. Have a look at the website. That's exactly what a consortium of universities in the UK we've got together, and with the British Geological Survey, and to look across that life cycle. So from the mining that we've been talking about today, but through the use, we've got business colleagues there, through the how do you manufacture so that you can recycle at the end of life? What are the good ways to recycle using environmentally friendly chemicals? Before you need to recycle, how do you extend the life of products? How do you reuse things? How can you repair things more easily? That right to repair. Go to University College London. They're running a fantastic big campaign on the right to repair. I think it's still going. You can fill in a little survey. So yes, make things have a long life. And then absolutely, that's a great challenge, great chemical challenge. As we bring these new materials into our economy, we've got to make sure they're not going out to waste at the end, so that they're coming back round in that recycled circle, and that we keep our new lithium and all the other battery metals like cobalt and nickel and graphite and all of these things. We don't only go for the super expensive things. We've got to learn to recycle all of them.
So what you've got there is you've got legislation that has pushed for the recycling, but you've also got, we've been using lead for many, many, many years, just like aluminium, copper, etc. Whereas it's only been relatively recently that technology has required the likes of lithium or the rare earth elements. So they're kind of relatively new in terms of us using them in any great volumes. And so that's something where we don't have time to hang around to work out how to recycle these. So that's why all of the research projects, as Francis has just mentioned now, are so important right now. We need to do the research and then we need to get that into industry fast so we can ramp things up to industry scale.
Okay, so I mean, we don't have a ridiculous amount of time left, but both of you seem to be saying as we go along, just more and more interesting things. So if you could stop doing that, that would be great. I jest. So, I mean, you know, you're talking about the fact that, I mean, we've spoken about the fact that this sort of our technology is part of everything we do. You know, we need these metals, you know, as it stands right now, all these elements. So as we go forward, like if we draw a line in the sand now and be like, you know, we're trying to be better, like what are some of the scaling issues, very briefly, that we might see if we're trying to be like, you know what, let's have more electric vehicles, let's do this, let's try these new technologies. Like what are the problems that both of you have, I don't know, fall asleep and wake up sad about in terms of this, not like your personal lives?
I don't know whether I wake up happy or sad, but I think for us as geologists, of course, the challenge that we need, 10 times more lithium in the next 20 years, that's not something to make us sad. It may be a difficulty for the manufacturers of batteries to think, how are they going to secure their responsibly sourced raw materials? But for us, that's great, because that's a fantastic challenge for us to go out and find the responsible sources of those materials. So let's stick with lithium. The really exciting thing in the last 5 years has been the realization that we actually have some lithium deposits that may be globally competitive right here in the UK, in the southwest in Cornwall. There are 2 companies, and they're busy exploring some different kinds of rocks and some underground brine, so underground water, to actually extract lithium. So we could have part of that battery supply chain here in the UK. So yeah, big challenges, but I think they're exciting ones for us to tackle in the scale up. More deposits, will take us into new kinds of deposits and new challenges in the extraction.
I like how that answer was essentially, you know what, it keeps me in a job, so I'm good.
But I think with that, Alex, it's a case where, yes, we could get really worried about this. In order for us to be able to reduce our emissions by 40% by 2030, which is only 8 years away. And as we just mentioned, it takes 30 years to go from finding a new deposit in the ground to mining it on average. So there's something that doesn't quite work with regards to these timescales here. But what this means is that for all of us who are working in chemistry, in geology, in engineering, in innovation in general, it's an immense opportunity for all of us. There's a paper that actually Francis, I think, very much contributed to, where we think that in order for the UK to meet our targets just with regards to electric vehicles, so in terms of moving from combustion-driven vehicles or power vehicles to electric vehicles over the next few decades, for us to do it just for the UK fleet and just for the vehicles themselves, we will need twice the annual production of cobalt, all of the neodymium, 3/4 of the lithium, and half of the world's copper supply, just for the UK. So in terms of the supply-demand gap that we are looking at the moment, it requires all of us to put on those thinking caps to think, right, as chemists, how can we separate those minerals and those metals in a more cunning way that not only gives us better production so we can produce more of these materials faster, but also does it in a way that doesn't endanger the environment, perhaps in a way that traditional processing techniques have done, and also means that with all of these non-renewable assets, because no mine is sustainable, we don't have any intention of putting the rock back where it came from. However, we can be mining and processing in line with sustainable development principles. So how do we therefore make sure that what we're aiming at is value for the future? So whilst using the material in the ground at that point in time, how are we creating a better future for the people and the environment that live in that particular area? That's what we're aiming at here. So it's an awesome and very exciting challenge for all of us that are involved in this space right now. And we need all the help we can get.
I love it. I love that both of you are able to spin my negative into a positive. I appreciate that. And of course, my final question, it's usually the most difficult one, genuinely. If you could give one takeaway to the people listening, what would it be? One brief key takeaway that you'd want them to go away with, maybe chat to a friend and be like, hey, I learned something today.
Respect the materials in batteries. So this is a battery podcast, but respect the materials in everything that you're using. They've come from the earth. It's not just some piece. You can don't just pop it in the rubbish bin. Really think about what's gone into that. Just have a little bit more respect. And I often say a circular economy is a careful economy. So just think about that. Ask where it's come from. Think about what you're going to do with it and where it's going to go. Please get it in the recycling. Take it to the waste electronics place and make sure it's going to go on into its next life. Don't just put it in the bin.
And I'll build on that and say, yes, respect the materials, because a lot of hard work has gone into extract them from the ground. So let's keep them in circulation for as long as possible. But also let's respect ourselves. Planet Earth is going to be fine with regards to climate change. The bit of this ecosystem that will not be fine is human beings. So the people who have got something to gain by working out how do we deal with climate change, how do we make sure we source all those materials for those batteries, etc., in the best possible way, are us as human beings. So we're doing it, actually, it's for quite selfish reasons. We're doing it for ourselves because planet Earth, ultimately, in geological timescales, is going to be fine.
That's right, everyone. Life is fleeting. We are but a speck in the timeline of this earth. We will live, we will die, and we will leave nothing. Yes. I hope you enjoyed this episode. Goodbye, everyone.
Yeah.
Okay, well, Sarah, Francis, I'll let both of you go and enjoy the rest of your day.
Okay, thank you very much indeed.
Bye.
Bye-bye. Thanks very much.
That's all for this episode of Brought to You by Chemistry. Join us next time where we will be in the driver's seat to find out more about electric vehicles and why the future of transport might need all of us to do just a little bit more maths. It was produced by Hiran Joshi and Elizabeth Ratcliffe and presented by me, Alex Lathbridge.